Welcome to Hot Chips 34. Keynote 1. Semiconductors run the world.
Hello, good afternoon. Welcome to the afternoon session of Hot Chips. So my name is Chris Drosanovich, and I'm the Hot Chips 34 co-chair, along with Ron Diamond, PC co-chair. We have a great program this year, and we're really thrilled to have Pat Gelsinger, CEO of Intel, as our first keynote speaker. Before rejoining Intel, Pat was CEO of VMware and was ranked Best CEO in 2019, according to a Glassdoor survey. Prior to VMware, Pat was president and COO of EMC's Information Infrastructure Products Division. But Pat actually began his career at Intel in 1979, and he worked his way up through the ranks and became its first CTO, and also served as Senior Vice President and General Manager of the Digital Enterprise Group. He managed the creation of key industry technologies such as USB and Wi-Fi. He was architect of the original 8486 processor, a landmark processor in the industry, and led many subsequent microprocessor programs, including key roles in the Intel Core and Intel Xeon processor families. Pat holds an associate degree from Lincoln Technical Institute, a bachelor's degree from Santa Clara University, and a master's degree from Stanford University, all in electrical engineering. He holds 8 patents, is an IEEE fellow, and serves as a member of the National Security Committee Telecommunications Advisory Committee. His keynote is entitled Semiconductors Run the World, and we'll be running the keynote shortly. Some advice today. So please go ahead and post questions during the talk on the appropriate Slack channel. At the end of the keynote, I will pick questions from this channel and pose those to Pat during the live Q&A we have afterwards. If you see another question in the Slack channel that you find interesting, please add a thumbs up so we get some indication of the audience interest in the different questions in the channel, so we can pick the most exciting questions to ask Pat. And also, we also ask, please make sure you state your affiliation in your username. And the easiest way of doing that is go to your Slack profile and edit your name to add your affiliation there, so we can see that when you're asking questions in the Slack channel. Okay, so this time I invite you all to relax, sit back, and watch the keynote from Pat.
Hello, Hot Chips. Great opportunity for me as the Intel CEO to be with you today and giving one of the keynotes this year. So thank you. I'm excited to be with you. And the last time Intel presented was 3 decades ago, when Gordon Moore gave the keynote in 1985, and he called the keynote Nanometers and Gigabucks. Wow, how the world has changed since then. So it's my pleasure to follow in Gordon's footprints. And, at the end, I'll mention that I gave a keynote about a dozen years ago. So here we are, geeks at heart, and ever more so, the world runs on semiconductors. So whatever we're doing on Hot Chips, it's going to be more important for everything going on in the world. And in fact, we just had the most important piece of industrial policy legislation, I believe, since World War II, that enables the full support of the US government behind the semiconductor industry. A huge piece of legislation that was passed with the CHIPS and Science Act, the largest ever investment in semiconductor manufacturing, the establishment of the National Semiconductor Technology Center, the biggest piece of legislation for science funding over decades that we've occurred. And together, these pieces are fully now in law, supported by the signature of President Biden. And it was one of the great honors of my career to not only help to move this legislation forward, but to be there for the signing ceremony. And then the president took a small group of us on a personal tour of the White House afterward. What a seminal moment for the semiconductor industry and for the United States and its investments, commitments, and the priority that it has for the semiconductor industry. And clearly, this idea of the world runs on semiconductors is so critical and has been seen through the COVID crisis and the shortages that we've seen. And that was a key factor in bringing this critical legislation across the line. But this idea of the role of semiconductors, and I like to call it the era of the superpowers, not nation states, but technology superpowers. Everything is becoming digital. Everything digital runs on semiconductors. In this period of time that we're in, innovation, growth, discovery, and we're seeing this magic that fundamentally allows us to experience the world in new and powerful ways. And we'll say the four superpowers: ubiquitous compute, connectivity, infrastructure, and AI. Each of them are powerful in their own right, but combined, they amplify, reinforce, and create an exponential impact associated with them. Compute, literally everything is becoming a computer. We're seeing it, in our thermostats, in our light bulbs, and not just on our desktops. Everything is now being filled by a computer. And since the 4004 began this idea of a stored program, computing capability, everything is becoming compute capable. Second, connectivity, connecting, sharing, being able to bring together every aspect of the infrastructure and the connectivity of not only people, but things. Today, about 60% of humanity is connected. By 2030, 90% of humanity connected. And now it's not just people, it's things being connected as well. Third, infrastructure. With the advent of cloud, you now have this ability to scale infrastructure. Literally, your credit card, you can buy a supercomputer overnight. This ability to scale is now being combined with edge that enables infrastructure with low latency and bandwidth. And that combination of scale and reach of edge, literally, we have unlimited access to high performance scale infrastructure capabilities. And finally, number 4, AI. The ability to make sense of this vast amount of data, to be able to create actionable insights. And these 4 together reinforce each other. The more compute I have, the more AI I can do. The more infrastructure I have, the more data I can store. And the more data I have, the more learning and training I can do. Each are reinforcing the other, and that's accelerating the pace. And we see the superpowers increasingly allowing us to bridge from the physical to the digital worlds across literally every aspect of what we do. And underneath everything digital, powered by these superpowers, is semiconductors. And we've seen that we've been in an era that more and more semiconductors are being enabled by the foundry business model. And the foundry model has enabled more and more access to semiconductor innovation than ever imagined. Right? And now we're seeing that this model of engagement is being used by more and more in the standards, the IP libraries, the ecosystem has created an era of semiconductors playing more and more vital roles across more industries. But we also see that this idea of a wafer foundry era is giving way to what I like to call the systems foundry. And if you think about it, the rack is becoming a system, and the system is becoming an advanced package of multiple die and chiplet. Literally, the system is becoming the advanced packaging technology of the future. And when I think about this, I think about it as a wafer foundry, essential, right? A fundamental enabler. But even the wafer foundry, we need more types of technologies across analog, display, power, a broadening set of the technologies at the wafer level, combined with advanced packaging. The board is becoming a chip now, and that advanced packaging in 2.5, 3D packaging, the interface standards of enabling chiplets that you can have hard and soft IP and chiplets that you're able to compose together on this advanced package. And then finally, the critical role of software. So we're moving from the wafer foundry era to the systems foundry era. And what does that mean? Well, now it means, boy, as we start designing and utilizing these, literally, we're going to be able to look at these set of technology capabilities to bring about next generation designs as a systems foundry. And this is exactly what we're out to enable, right, with the Intel Foundry Services, is to participate, enable, to be a driver for the systems foundry era, creating this broader set of technologies that enable the design community, the ecosystem, to be able to innovate at a scale not achievable before. But underneath it all, what's it rely on? Moore's Law, right? And very simply, Moore's Law, this continuing doubling of transistor, capability as the dimensions shrink over time, fundamentally the driver of everything that we've been able to accomplish. The reason chips are hot is because Moore's Law enables it. And, when we think about the era of Moore's Law that we're in, Intel's thrived to be the custodian, the company that just keeps moving Moore's Law forward. We provided this technology backbone that's enabled this period of human innovation and wealth creation. And we're still right in the thick of it. And as we think about Moore's Law of the future, it isn't just that the world wants more semiconductors, but we want more powerful semiconductors. AI models are getting larger, cloud is getting bigger, and together, we continue to see that every experience, and whether it's, creating virtual economies or more metaverse-like experiences, the digital twins of everything, more and more powerful computing. But can it continue? And we fundamentally see that today, we're about 100 billion transistors on a package, and we see our way clear to getting to 1 trillion transistors by the end of the decade. Wow, that's a pretty bold statement. Well, with RibbonFET, we have a fundamental new transistor structure that we're just about to come into that we believe continues to scale through the end of the decade. Second, with PowerVia and being able to use both topside signal and backside power delivery, we believe we have a new power delivery architecture. Third, with EUV and high NA, lithography looks like we've got a good path through the end of the decade. And as we've already touched on, 2.5 and 3D packaging, we're enabling us to have sort of the sweet spot of die size being composed with essentially low-end process technology being applied to packaging. So 2.5 and 3D composition. And those four taken together, RibbonFETs, high NA, next generation of EUV, 2.5 and 3D packaging and power delivery, we're on a path that we believe 1 trillion transistors by the end of the decade. And as I like to say, we're not done until we've exhausted the periodic table. And silicon has just been this magic, right? The most, commonly available material on Earth. It's rugged, it's manufacturable, right? It has this semi property. It can be made to be a conductor, right? Or an insulator. And we started with silicon, but then we've just been adding and adding and adding to it. Oxygen, aluminum, boron, phosphorus. But now we've continued to scale and use more and more of that periodic table. And today, an advanced semiconductor is using almost 1/4 of the periodic table and maybe 1/3 of the periodic table during the processing and manufacturing. And we're not done because there's still a lot of effects and a lot of the periodic table left. We are going to keep innovating in silicon until we have exhausted the periodic table. That's what we are at Intel, this relentless pursuit, right, of that continuing progress of Moore's Law. And there's a lot of chemistry, a lot of physics, and a lot of the periodic table yet to go. But we've also noted that the world is changing. And the role for complex systems at a package level, and even if we go back to the earliest days of Gordon's predictions, where he sort of foresaw this day of reckoning where we'll need to build larger systems out of smaller functions to deliver customized heterogeneous capabilities. And This is where 2 and 3D packaging technology steps in, where we give architects and designers the tools to further apply the right transistors to the right problem, for power, RF capabilities, display capabilities, as well as the most advanced logic capabilities, the most advanced memory. And being able to bring those together is a key factor of this next era of Moore's Law. And that's exactly why our packaging technologies are so critical to the future. And things like EMIB, embedded multi-die interconnect bridge, being able to tie more things together or cram, capabilities together with high performance, and being able to not be reticle limited, but being able to tie more die together and sort of hit the sweet spot of density curves and performance curves and cost curves simultaneously. And EMIB, a critical enabler of that, or technologies like Foveros that enables active logic on logic silicon stacking. And essentially, we're creating logic transistors in 3D. And we have our next generation capability starting to take advantage of these, where we're combining these together in products like Meteor Lake, right, which are being brought to the marketplace next year. And beyond that, Arrow Lake and our second gen of 3D packaging technologies that are starting to take advantage of these types of advanced packaging capabilities. And tying all of those together are products like our highest end high performance computing. And here I have a Ponte Vecchio, which is 47 active tiles of silicon in a single package and over 100 billion transistors. And this is the core of the 2 exaplot machine from Aurora. Advanced packaging, advanced silicon coming together at a system scale capability for the highest performance computer that's ever been built. But of course, I also mentioned this idea of standardizing how we fit the pieces together. This is another area that I see as fundamental to the systems foundry era, where how do we compose these different pieces together? And Intel has a long history. And I remember the role that we played in bringing PCIe Express to the marketplace, the standardization for how we fit systems together. Well, now we're doing that at the chiplet level and taking a monolithic system on a chip that could be constrained in die size, cost, or power, and being able to disaggregate it into a solution that takes advantage of not only the advanced packaging, but the standard mix and match capabilities that UCIe will enable. And we're excited about this because, different process technologies will be optimized for different functions: power, RF, analog, advanced logic, memory. But we also then need to tie these together in a easy to use, composable fashion that gives the designers the abstractions that enable them to do more complex things without the detail of each execution, and harden IP at the lowest chiplet level. And we're currently working with the ecosystem to create this standard, and it's building on, CXL is the technology, and this is what the Universal Chiplet Interconnect Express, or UCIe consortium, is all about. And we launched it earlier this year. We're thrilled to have partners: ASE, AMD, ARM, Google, Meta, Microsoft, Qualcomm, Samsung, and TSMC, all coming with us on this journey to establish the chiplet ecosystem at scale. Chiplets enabling us to take advantage of that advanced packaging, being able to use multiple foundry technologies across different vendors, different fabs, and compose it together into complete system solutions. And overall, this is as disruptive, we believe, to the future of design as PCIe was in the early 90s when we launched it. And with that, we're excited to be positioning our foundry offerings to be a core enabler of this as we bring together, chiplet design across the industry. And the Intel Chiplet Studio suite of technologies will enable it across multiple architectures as well, including x86, ARM, and RISC-V. And you can see this sort of sea of accelerators being combined with our advanced capabilities like Xeon to allow our customers to build an optimized solution for their specific needs. So that's a bit of a view of the future, but also let's take a view of the past. Just before Gordon was giving the keynote was when we introduced the Intel Pentium processor. Clocked at an amazing 133 megahertz and a whopping 3.3 million transistors. And in some regards, those were the easy days. Living in them, I don't think that they were fully easy, but it was also in many respects, hardware was the center of the world and silicon was where it was at. And this ability then to just cram more, and we were in the Dennard scaling era of Moore's law, in many respects was somewhat straightforward, easy. No, hard, but still very contained to the core of what we were doing in silicon. But oh, how the world has changed. And the role of software, as the Intel CTO, Greg Lavender, likes to say, software is the soul of the machine. And customers benefit from these software optimizations. They standardize and they access the capabilities of silicon through software and APIs. So the fourth component of our system foundry strategy is software, silicon plus software. And to bring the systems approach to life, we must lead with a software first mentality. And this is a center point for how we are rebuilding Intel for the future and what we believe is the heart of what we're doing. And we call it software defined, silicon enhanced. At the top layer of the software stack, is market making technology built on foundational middleware, right, and application software, all sitting on top of this, at the core enabling level of what we do for operating systems, virtualization, systems drivers, BIOS, APIs. We need to deliver that complete solution for the designers of the future and enhance it with new hardware and silicon capabilities coming underneath it. And that's what we mean when we say software defined, silicon enhanced. The software interfaces are precious. They take longer to establish. The software has become, in many senses, the center of innovation. And in fact, in the early days, when I was still designing chips back in the 46 and Pentium days, the hardware industry swamped the software industry in size. Well, what's happened? The software industry now swamps the silicon industry in size. And, estimates show that we crossed over, in the early 90s where the software industry became bigger than the silicon industry. And by 2026, estimates say it's 3 times bigger. In other words, the software has become way more important. And we have to treat those as the sacred interfaces that we then bring hardware underneath. And that's where our silicon has to fit into it. And that's why we say this is a critical element of what a systems foundry is in the future. Well, this is the first time since 2012 I was able to join the Hot Chips community. I thank you for that opportunity to be speaking today. And this was a slide from my Hot Chips presentation a decade ago, just as I was becoming the VMware CEO, and how we saw this convergence of cloud and big data. When I said that a decade ago, it wasn't nearly as obvious as it is today. And even in this period of time, we were in the infancy of what cloud adoption was going to be and big data. It was clear that hardware and software were coming together in a fundamental way. That's why we're pretty excited about this next phase of innovation. And as we've talked about the Intel Foundry services, we view it as a systems foundry, as an open systems foundry, where system software, chiplet standardization, 2.5 and 3D packaging, all of these coming together to enable the next era of innovation. And this is what systems foundry is all about, the consolidation of all of those pieces coming together to enable a broad community, an open ecosystem of innovation to occur. Of course, what will we be talking about 10 years from now when we're here looking at the next decade of Hot Chips? Well, hopefully we see that this idea of a wafer foundry giving way to systems foundry, but we also see that many of the challenges, things like power density, power delivery, almost every design that we have is now power limited. We're going to have to do co-optimizations across the hardware and software domain, also across multiple chiplets and how they play together to be able to manage complexity, shorten interconnect, manage not just at the chiplet level, but across chiplets and across the 2.5 and 3D package. Literally, the systems problems of today have become the chiplet problems of tomorrow. And we see enormous areas for continued innovation, work, collaboration for the future. So, as we look to that period of time, there's just so many great opportunities for us together to continue innovating, in power, co-optimization, system design, hardware, software. And a systems foundry is about bringing these pieces together for that future. 75 years ago, Walter Brattain and John Bardeen made the first working transistor. A half a century ago, was when semiconductors started to really ship commercially. We have now the 50-year anniversary of the 4004 with compute now touching everything. And the market today for semiconductors about $650 billion and expected to cross $1 trillion by the end of the decade. Every aspect of human existence is becoming more digital. Everything digital runs on semiconductors. There's never been a better time to be a technologist, never been a better time to be in the silicon industry. Thank you so much for the opportunity to join you today.
Well, it was a great keynote. Very excited to have Pat here today, and he's here live. So just a few comments before we switch over to Pat. Please ask questions in the Slack channel and make sure to have your name and affiliation on there, and we'll take a bunch of questions. We have a bunch queued up already. I can just visualize in the old days there'd be a whole queue standing at the mic waiting to ask questions, but we're doing that virtually today. So hopefully Pat is online. And
thanks, Lance.
Okay. Hi, Pat. I can't see you here, but oh, there you are. Great. Thanks for the great keynote, and thanks for making time, spend time with us here today. I know people are very excited to ask you some questions, so I'm going to dive right in. And
good, let's go.
Okay. So the first question is up from John Masters from Google, and I think this is in the context of talk about the CHIPS Act and also the move to being a systems foundry from wafer foundry. And so John asks, what are your thoughts on the importance of neutrality in terms of equal access to all comers, both internal to Intel and external companies? In other words, how do we get to a point where such investment allows you to offer a service that your closest competitor would be comfortable relying on?
Yeah, maybe three different aspects to this. The first one is, I do think there needs to be, much broader access, both at the university and at the startup level, right? So that is like we're building our foundry, systems. I want to see us go, I've said, two orders of magnitude higher shuttle count, so that, startups, universities, et cetera, can be building, those capabilities so that we're fostering the next generation of semiconductor companies and ideas in the process. Then it's sort of the question sort of asked, how do you make sure then that you have equal access to it, to those capabilities when you start to build real companies? And our expectation is that we will be, creating, cleaner separations between the Intel products and the Intel foundry, so that the foundry services customers, view they have absolutely equal footing to the product company of Intel to be able to have wafer commitments and capacity corridors, access to leading technologies, the wafer, the packaging, and at the software level. Obviously, some of the things like the chiplet standards, UCIe, right, start to create more of that open ecosystem environment as well. So I'll say that's absolutely the intention that we have as we build out these capabilities. I'd say, at the end of the day, some of these things just come down to business terms. So, we're going to be, committing capacity corridors. We're going to have, similar to the other foundry players, we'll have, similar T's and C's associated, with that. I'm not happy with some of my foundry capacity corridors that I have today. We've been fighting to get more, for those. So I don't think, the idea of bringing more diversity to the supply chain, more geographic diversity, as well as us stepping in for more leading edge capacity. If there are more choices, that's good for everybody, and we plan on being one of those choices for our foundry ecosystem.
Great, thanks. Yeah, so leading in, picking up on one thread here, the next question is from Stephen Bates, Identicom. How do standards like UCIe impact Intel's thinking on systems in package? Will UCIe become the de facto interface between chiplets and lead to a mix and match approach where end customers can combine chiplets from different vendors and get those packaged by a third party?
Yeah, that's my expectation. That UCIe becomes like PCIe. When you thought about PCIe, you didn't necessarily say, hey, was I getting this component from Chips and Technology, this component from YTech, or so on. If we go to some of the historical names and companies, you just said, hey, we're all building the PCIe, and it gives a level of interchange for it. We expect UCIe to be the equivalent, and with that, you may say, hey, I'm getting 2 of the chiplets from Intel. I'm getting 1 of the chiplets coming from a TSMC factory. Hey, maybe the power supply components coming from TI. Maybe there's an I/O component coming from global foundries. And of course, Intel has the best packaging 3D technology. So they're going to be the one assembling all those chiplets together into the marketplace. But maybe it's another OSAT provider as well. So we do see the mix and match. And when I say the rack is becoming a system, the system is becoming an advanced chiplet-based SOP system on package. That's exactly what we mean and how we see it evolving.
Yeah, I'll just add my own question on there. So UCIe is a protocol level interface, but how about the physical packaging? If different system foundry houses package differently, do you expect chiplets built for one packaging system or one foundry to be portable to another, or how do you expect that to play out?
Yeah, I do think there's going to be some aspects of this that are going to take, they're going to be natural extensions, to, PCIe essentially was a electrical and protocol standard before it became, a socket interface as well. And I think some of those things will evolve similarly. I think it's a huge step forward, but in no way is it the end of the discussion. In many senses, it starts to create the ecosystem for system on packages, and this is one of the Ponte-Vecchios where, hey, every one of these interfaces is custom today, right? Other than, like HBM, which is a quasi-standard, right, based on the DRAM specs, but, everything else is, I'll say custom, for us. In the future, we see UCIe becoming, the dominant, right, standard in that space. But even then, I think there's going to be others that need to emerge. And right against that, I think the packaging physical interface standards are going to become more important as well as you start to really create a mix and match ecosystem across different OSAT and different foundry partners.
Okay, great. Next question. This is from Amira Chana at the University of Cambridge. Have you given any consideration for IFS to host open source wafer shuttle programs such as seen with eFabless and Skywater?
Overall, and that was my earlier comment to the first question. That's my expectation. That there's, that we're just going to ramp up the shuttle capacity. Now, like any shuttle program, how do you fund it over time? And one of my objectives would be, some of this. Hey, we're going to fund from Intel, but we're not going to be able to scale it to the degree that I would hope to see it scaled over time. And that's where things like, in the CHIPS Act. There were 2 other major elements of the CHIPS Act beyond the manufacturing funding. One was the NSTC funding, the National Semiconductor Technology Center. The other is the NSF funding. And in both of those cases, I would hope, that we're able to start taking some of those funds for being able to scale the shuttle program for essentially pretty broad access to the academic community, that we're able to, instead of running, 1 or 2 shuttles a quarter, we're able to start running, tens of shuttles per quarter, and then maybe hundreds of shuttles, per quarter that we'd be able to scale up to. And the results of that is that there'd be a lot more access, to a range of semiconductor technologies from very leading edge, right, to, more mature nodes. but also being able to overlay that on some of the advanced packaging technologies as well.
Great, thanks. So next question's from Cliff Young at Google. He's saying, my hoped-for subtitle for your keynote was, Intel is back, baby. Here's how we're going to do it. I think the root of Moore's law is the progression of process nodes. Can you talk about the steps you're taking to return Intel to dominance in silicon processes? I think the implications are huge, not just for the tech industry, but also for the USA and the whole world.
Yeah, well, first I agree with that, the sentiment behind that question entirely. Part of the reason I came back to be the CEO was exactly that. A healthy Intel, right, is a powerful underlayment for the technology industry. It's restoring the legacy of, I call it the Trinity, Moore, Noyce, and Grove at Intel, and getting ourselves back. And with that, we laid out what we call 5 nodes in 4 years, where, we're going to have the most torrid pace. And torrid is my favorite word since I've come back to Intel, right? Setting this very aggressive, data-driven, intense pace. So we believe by 2014, when we introduce our Intel 20A technology, that is very competitive with anyone else in the world. 18A, when we launch that late in 24, we expect that that's best in class in the industry. So we think we have a path that we're on now to have, a leadership position for Intel. But then, of course, it's continuing that for the decade. And we have the nodes lined up through the rest of the decade, and the transistor architectures, the lithography steps, and as I touched on in the keynote, also leveraging, the power delivery network, the backside power delivery network. So you solve power delivery, signal congestion, transistor architecture, lithography, I'll say, sort of the core limiters of more time. You combine that with essentially, 3D packaging technologies, which are essentially low-end process technologies. So essentially, you've moved from things like wire bonding to wafer-on-wafer techniques. And the combination of those, we see ourselves, with a fairly clear path to 1 trillion transistors, in a package like this by the end of the decade. So, we feel pretty comfortable with that path. And as I've said on quarterly earnings calls over the last few quarters, that we're on or ahead of schedule on the 5 nodes in 4 years. And we're now building a lot of momentum for the technologies that come after that, because exactly like the questioner asked, hey, a healthy Intel is good for the tech industry broadly.
Okay, great. So next question, another one from academia. Grace Din at Berkeley. With a much greater diversity of chip architectures, often being used together in concert, chiplets, etc., and the increasing integration of hardware and software, how do you see the roles of different actors, big vertically integrated cloud companies, hardware companies, software companies, academics, open source projects, evolving in the next decade?
Yeah, I think it's a great, it's a great question, and that's very much what we're aiming at when we talk about systems foundry, right? Where all of a sudden you're bringing many of these things together. It's sort of, it almost feels like you have a black hole worth of energy coming into a small, location, because you are getting to these very, small, form factors, and it's going to be, optimizing power delivery. Bringing the RF analog components very close together. You'll have high, performant, low latency interfaces to, large pools of memory in those environments. So all of a sudden, it's sort of like, oh, I can do almost anything in hardware, and hardware has now become, the silicon composite. But against that, and as I wanted to highlight there, and I often say, why did God have me run a software company for the last 8 years before coming back to Intel? Well, people develop software, and silicon has to come underneath it. So those hardware components and those chiplet standards then also need to consider, right, the composition of the critical software components that come with it, right? And that combination, that co-optimization of software and hardware becomes essentially the pathway to being able to bring such complex systems, to the fore against stable, proven, composable software interfaces that silicon supports in a complete way. I do think there's going to be all sorts of new areas of co-optimization across those subsystems, and obviously we're going to need the next generation of EDA tools to, be considering it. When I was writing EDA tools, it was, hey, can I synthesize this one logic tree? Well, now, okay, that's sort of easy. Everybody can do that. Now it's, can I be able to synthesize this complex system of hardware and software components across multiple technology domains into usable systems? So it's going to be a whole new class, I believe, of EDA tools required, to enable us to tackle these system problems at scale.
Great. Yeah. So just following on this question, my own question here is, so Intel grew up in the microprocessor era where the standard microprocessor was the product. Now, when you have these specialized packages, they go directly to the end product. There's not a standard part in the middle. So how do you see, that's part of the change of systems foundry, but how do you see that change in the industry from more horizontal to more vertical playing out? And I think that was part of the question, the different actors in that new world.
Yeah, and I do think that all of a sudden you're going to see sort of this reforming, but we've seen it over and over again, right, in history, where hey, the flip-flop used to be the product, right? And then you compose it, and then you create a new layer of abstraction. And to some degree, these subsystems now are going to become extraordinarily powerful, right? But you're going to be accessing it through new layers of abstraction, where to some degree, hey, I don't know how my parallel Python is being fully implemented underneath this, but I know it is. And now that becomes the subsystem that I'm now applying to my healthcare system or to my AV system and my autonomous vehicle or so on. You're going to be abstracting at much, much higher levels. And we're going to be needing to synthesize and deliver these packages and solutions. And when we think about one of these components in the future, we have ones on our roadmap now that are CPUs, GPUs, high performance IPUs. What is a CPU in the future, right? It's not even clear anymore. And, I do believe that you still have the, scalable operating system ends up being the traffic cop, right, across a lot of these subsystems. But these subsystems become more autonomous, right, with higher levels of programmatic access to them, enabling them to tackle problems that you couldn't even dream of before.
Great. So I think the next question is interesting follow-on. Umar Darbaz from NVIDIA asks, vertical optimization and hardware-software co-design requires us to democratize hardware and have processes for easily taping out prototypes we can run software on. Will Intel provide independent people and groups with the tools and guidance on how to use it as a foundry? So in this new model, are you going to help the customers get to the solution here?
No, simple answer is yes. Now, obviously, when this is sort of goes back to one of the earlier questions, our foundry customers will be foundry customers, right? And they're going to have, access to a portfolio of IP libraries. Many of those IP components will include the software components that goes with them, right? Some of those will be hard IP, some will be soft IP, some will be chiplets that are going to go into this rich 2.5 3D, package solution. And I'm also going to have the Intel products teams that are designing using many of those same components as well. But we'll have third-party IP providers, the Synopsyses, et cetera, that are providing IP blocks, ARM, and companies like that that are, bringing those components together. So, somebody like an NVIDIA designer, is going to be able to say, hey, do I want to use some of the Intel product group blocks? I'll be making those available through our foundry, business. Do I want to, essentially design those myself, or do I want to leverage third-party IP blocks? And the idea of a systems foundry is I'm going to have that complete canvas available to me as I go to compose these systems. Obviously, if they're using some of the Intel product blocks associated with that, like NVIDIA, they're using Sapphire Rapids in their next generation DGX system. Well, hey, in the future, they'll be able to buy it as a product or potentially as a chiplet that they might compose into a system on package that might include, a Hopper component or something else. We do expect that kind of design. And again, if you think about that, you sort of say, well, they could do that in a PCIe world, right? They could absolutely do that at the board level. We're saying going forward, they're going to now be able to do that at the systems foundry level into an advanced packaging solution, and we're going to be making that available. And obviously, if I have the best packaging technology, I have the best transistor technology, I'm driving the industry standards for how these pieces, the Intel business is going to do just fine in the process, and a lot more people are going to be innovating on top of those core technologies that we provide.
Okay, great. Yeah, next question is from Claire Castellanos at the Ketchum Agency. She asks, how will you realize the systems foundry mindset in the very near term? What are the key moments the industry should watch for from Intel?
Yeah. Well, one of them just happened in the formation of the UCIe group, right? To me, that was sort of like, okay, right, Intel is back, because, Intel has a long history, USB, one of those that I was deeply involved in. When my granddaughter plugs her USB stick into the PC, she says, "Thank you, Papa." Right? You just sort of heartwarming, but that's what we do. We create these platform technologies that people build on and participate in, and rich ecosystems emerge. And if we're a driving force for these open ecosystems, hey, we do great. And I'll say, I really believe that in the heydays of Intel and PCIe, USB, Wi-Fi, we created ecosystem standards that the industry benefited from. And I think the launch of UCIe, which we drove and created, was one of those moments that you can say, this is the Intel I used to know, right? A decade or two ago, we're back to going and doing that. And I think every day that you see us now saying, okay, we're going to build open one API interfaces into our core blocks. Okay, you have more composability into these software layers that we're going to be delivered. We're going to be driving some of the open AI standards, and you're going to hear more about that at our Intel Innovation Conference coming up next month. As we're saying, hey, these are the open interfaces for how people will be able to access advanced AI technologies as well. So each one of those, I think, are markers. I think the questions around the shuttle and the foundry capability are other markers as we see progress in those areas. But at the end of the day, the industry has to be able to look at us and say, I can do my innovation on top of those Intel capabilities, whether that's foundry, packaging, or products, and I can do my best innovation in that. That's what we're off to enable and achieve.
Oh, great. Yeah, actually, the next question, I think, again, from John Masters at Google. I think he left the line, went back, and got to the microphone again. He's asking, can you speak, and this is building on the comments about UCIe you just made, can you speak to the kinds of solutions you foresee being built through UCIe? Today, the SoC ecosystem is very AMBA-centric. How do you see things shaking out as traditional SoCs are split out into chiplets?
Yeah, and I think you're probably poking on the right things. I think some of these things, what's going to be the performance level, the power level, and that's why I sort of say, hey, I think UCIe is sort of the middle of the road as we sort of view those, but I think there are going to be lower power, lower performance standards that need to emerge. You probably do custom, some custom things for higher end solutions as well for that composability that occurs. So I do think there's going to be some amount of gestation cycle as the industry collectively decides where the the right partition and the the weight versus power latency kind of trade-offs of those different chiplet architectures will be, and where the rich areas of ecosystem swim lanes will emerge. So I say one of it is, hey, I don't know, right? Would be part of my answer to the question. That's why the fun of creating standards like this will enable the industry to start to do that innovation. I'll say, hey, the combination of what we've done with like CXL and UCIe, I think are good starting points, but I view them as starting points. And as the industry starts to adopt those, how are we going to access memory, through those solutions? Memory hierarchy is always a, super important aspect. Are we going to be power sensitive enough as we go through those standard interfaces? And we know that ultimately power and, is the determinant now of how we partition our chips today and how we design them today, inside a power envelope. So I think those are going to be some of the areas that, will help decide how these areas and interfaces evolve. And in the meantime, hey, I encourage people jump into UCIe, start telling us where it's broken, and let's go start addressing those things in version 2 and 3 of the spec.
Yeah, great. Yeah, and also just remind attendees, we had a great tutorial yesterday on CXL, which is going to be later over UCIe, so that's a great start. And hopefully, maybe upcoming hot chips, maybe we'll have a tutorial on UCIe as well. I think that'll be a good topic.
I think so.
So I want to make sure we leave some time for you to wrap up at the end, but maybe one more question that's dear to my heart from Kevin Cruel at Tirios Research. What can the industry do to get more students interested in building chips, semiconductor research, chip design, and hardware?
Hey, thanks, Kevin. Great question. And one of it is, I just gotta, I have to give a little advertisement for the Midwest. When we announced the opening of our Ohio facility, I stood on stage, the governor was here, I said, today ends the Rust Belt. Today begins the Silicon Heartland. Well, you can feel the flags, in the breeze, et cetera. But the enthusiasm that we've seen from the university systems is largely the tech boom occurred in the coast. It didn't occur much in the middle of the nation. And this enthusiasm that's been unleashed as a result of that has been nothing short of spectacular. I mean, I'm getting regular updates from the major Midwest universities, Michigan State, Ohio State, Purdue, Case Western, et cetera, all about how they're building their semiconductor and manufacturing credentialing program and so on to give us that supply chain of talent that we would want into the future. I also think that the NSTC, the portion of the CHIPS Act around science and technology centers, research funding as well, is another kickstart. All of a sudden, you're sort of saying, hey, there are real dollars on the table for research grants, research programs, expanded NSF programs as well. I think that's going to be a kickstart as well. And we're seeing very similar, I was very involved in helping to draft the EU CHIPS Act. And we're seeing very similar kind of motivations in the EU. And now all of a sudden you're seeing across the world. Literally, I was on the phone last night with some of the key leaders in Japan. Right? What does that look for them? So I do think there's a resurgence of interest in, these core areas of manufacturing science, semiconductor and designing semiconductors, co-optimization of hardware, software, systems, in addition to what we've seen in some of the software and AI areas over the last decade. So I'm super optimistic here, just because the energy I'm seeing that's gotten unleashed. And, the CHIPS Act was, I'll call it the domino that marked this turning point. This is the most significant piece of industrial policy legislation in the U.S. since World War II. This is big, right? And I think it does unleash energy, for people to start to rethink what has been going down in the U.S., as a reversal. So I just say, hey, hot chips in the future is going to be a lot hotter because we're going to have a lot more cool things that we're talking about.
Look, that's great, Pat. So I just want to say thank you very much for making time for us today. And also, if you have a minute or two for any final closing remarks.
Well, thank you. And by the way, I think I misspoke earlier in the keynote that I'm the first Intel to speak in 3 decades. I'm the first Intel CEO to speak since Gordon Moore. So just to clarify that a little bit. But building on that, hey, part of the reason I came back to the company was to build on the legacy of Gordon, Andy, and Robert, and their huge seminal impact they played on creating silicon. And, this magic element, that God gave us in the periodic table that we've just been, adding more and more capabilities to at the chemistry level, at the physics level, understanding more and more. And this idea that we can, in fact, have more and more, that we can continue to press Moore's law and that our systems are becoming so sophisticated. The ability for us now to have 10, 15 million neural neurons being simulated now for some of our research projects. That we're able to start talking about hundreds of qubits. Starting to operate in quantum systems and be able to talk about the systems foundry that's going to open that innovative platform up. For millions of developers into the future. And in light of that, hey, it's been a decade since I've had the chance to be at Hot Chips. I'm honored to be able to join you this year, and I look forward to being a regular part of it, and hope you enjoy the other Intel papers as part of it, because, we have a lot of chips to build in the future together. Thank you so much.
Thank you so much, Pat. Thank you for your time.